Hello everyone. Today we are going to discuss the magnetic properties of an atom. So let's get started. When we talk about magnetism, most people immediately think of a bridge magnet or maybe the compass needle, but the real story of magnetism begins much deeper at the level of individual atoms. In this lecture, we are going to look at how a single atom behaves when placed in a magnetic field. To keep things simple, we will ignore interactions between atoms and focus only on one isolated magnetic moment. That is why we can build a clear picture of the basics before moving on to more complex systems. This approach will help us understand key ideas like magnetic susceptibility, diamagnetism, and paramagnetism, all of which emerges from the way atoms respond to the external field. And it all begins with a simple but powerful question. What happens to an electron's energy when its spin interacts with a magnetic field aligned along the z-axis? So let's start chapter 2 as isolated magnetic moments. First of all, we will talk about an atom in a magnetic field. Then we will talk about the magnetic susceptibility contributions. Then we are going to discuss diamagnetism and paramagnetism, the ground state of an ion and Hund's rule. Then about the application of paramagnetism in case of adiabatic demagnetization. Then finally about the nuclear spins and hyperfine structures. So let's begin with the first topic, that is an atom in a magnetic field. Now in the previous video, we have seen that the electron's spin in a magnetic field parallel to z-axis has the energies equal to E is equal to g mu b times ms, where g is the Lagrange factor and its value for electron is equal to 2, and ms can take values plus minus half. So therefore, the energies will become plus minus mu b. Now, in addition to the spin angular momentum, the electron in an atom also possesses orbital angular momentum. So, if the position of ith electron in an atom is Ri and it has a momentum of Pi, then the total angular momentum is given by h cut times L is equal to summation over all the electrons and then Ri cross Pi. Let's give numbering to these equations. So therefore, the Hamiltonian for this atom will become H naught equal to summation over all the electrons from 1 to z and pi square divided by 2m plus the potential energy term of ith electron. Now let's apply the magnetic field B such that B is equal to curl of vector potential A. Now, as you must have studied in electrodynamics, that we can choose a gauge for which this vector potential A is equal to B cross R by 2. Also, in the previous video, we have calculated the new kinetic energy for this charged particle when it is placed in an external electric field and magnetic field. So that is given by Pi plus E times vector potential whole square divided by 2me. So therefore, the perturbed Hamiltonian in the presence of external magnetic field will become H is equal to the new kinetic energy plus the interaction potential between the spin and magnetic field given by B dot S term. Now we can use equation 5 and equation 2 in this unperturbed Hamiltonian to simplify this square term. So therefore our perturbed Hamiltonian will become, so the first term here represents the unperturbed Hamiltonian H naught. The second term represents the interaction energy between orbital and spin angular momentum with the magnetic field, and the third term has b raised to power 2 and it corresponds to diamagnetic contributions. This result I have written using equation 5 and equation 2. So therefore the simplification will give you, here the dominant perturbation to the original Hamiltonian H naught is usually the second term, that is this mu b L plus gs dot b, but we will see that sometimes this term it vanishes. The second term represents the effect of atom's own magnetic moment and is known as paramagnetic term, while this third term is due to the diamagnetic moments. We will discuss these contributions in greater details in upcoming videos. Now let's talk about diamagnetism. For a diamagnetic substance, a magnetic field induces a magnetic moment which opposes the applied magnetic field that caused it. All materials show some degree of diamagnetism, which is a weak and negative magnetic susceptibility phenomena. This effect is often discussed from a classical viewpoint, that is, the action of the magnetic field on the orbital motion of electron causes a back EMF, which by Lenge's law opposes the magnetic field which caused it. But the phenomena of diamagnetism is entirely quantum mechanical and should be treated as such. So let's try to illustrate this effect using quantum mechanical approach. For this, consider the case of an atom with no unfilled electronic cells, so that the paramagnetic term in the perturbed Hamiltonian can be ignored. And if the external magnetic field B is parallel to the z-axis, then the cross product of B and R will only have the components along y and x directions. So therefore, B cross R whole square will give you B square times x square plus y square. So therefore, the perturbing Hamiltonian in the case of diamagnetism will become E square B square divided by 8me times x square plus y square. So the first order shift in the ground state energy due to the diamagnetic term will become as delta E naught is equal to E square B square divided by 8me, and then summation over all these electrons, and then the expectation value of xi square plus y square on the ground state. Now we will assume a spherically symmetric atoms for which the expectation value of x square is equal to expectation value of y square, and which is equal to 1/3 of expectation value of r square. So therefore this first order shift in ground state can be written in terms of the expectation value of ri square as As you must have studied in the statistical mechanics that the magnetization is given by the partial derivative of Helmholtz function with respect to the magnetic field, and in this case, if we consider that there are n ions in a volume of V with all electronic shells as filled, then this Helmholtz function in this case will become n divided by V times delta E naught. So therefore this magnetization will be given by this, and differentiating this with respect to B will give you minus n E square B divided by 6m V, and then summation over all electronic states, then the expectation value of Ri square. Now using this we can extract the diamagnetic susceptibility as chi is equal to m divided by h, and which is equal to mu naught m divided by B. Now if we substitute m, then we will get chi as. Now this expression has assumed that the first order perturbation theory. This diamagnetic susceptibility are usually largely temperature independent. This is it for today, and in the next video we will talk about paramagnetism. Thank you so much for watching this video.